This video will accompany the Chapter 10 notes, Part 2. Section 10.2, Quantitative Response, Comparing two means. The central limit theorem for a difference in means. When choosing random samples of size n1 and n2 from two populations, the distribution of the difference in means has the following characteristics if we have independent random samples. The center of the sampling distribution will be centered at mu1 minus mu2. The formula for the standard error is given on the screen, and if the populations are normal, or the sample size is sufficiently large, the distribution will also be reasonably normal. The larger the sample size, the more the sampling distribution tends to a normal distribution. A normal distribution is a good approximation as long as n1 and n2 are both greater than or equal to 30. Confidence intervals for a difference in means. Recall our goal is to learn how to translate the information contained in a single sample to learn about the parameter. The most simplistic way to do this is to use a point estimate. A point estimate is a single value estimate of the parameter we are interested in learning about. It is our best guess. The statistic from the sample can be used as a point estimate. So in this case, since the parameter that we're interested in is mu1 minus mu2, the point estimate will be x bar 1 minus x bar 2. We know due to sampling error that the statistic, or point estimate, is rarely exactly equal to the parameter. Instead of using the point estimate, which is a single number, we can use an interval estimate. An interval estimate gives an interval of plausible values for the population parameter. One common form of an interval estimate is known as a confidence interval. So recall that the generic formula for a confidence interval is the statistic plus or minus the margin of error, where the margin of error reflects the precision of the sample statistic as a point estimate for the parameter. The margin of error is constructed by taking into account the standard error and the percentage of intervals that would cover the parameter based on the behavior of the sampling distribution. So how do we calculate a confidence interval for a difference in means? Take a moment and read pages 17 and 18 on your own. Page 17 will go through the steps of calculating a confidence interval for a difference in means. You should notice that this is very similar to all of the other confidence intervals that we've calculated, with slight changes to account for the fact that we have two parameters, mu1 minus mu2, that we're interested in learning about. On page 18 is a fully worked example so that you could see how to calculate one of these by hand. For your exams, you will need to be able to read computer output to calculate these, similar to what we did for a difference in proportions. After you read these two pages, come back and we'll look at an example where we read computer output. Now that you've read the example on page 18, let's see how we could use Minitab to help us answer the question. So as a reminder, the example reads, suppose that a simple random sample of seniors are selected from two high schools in Richmond, Kentucky, 61 students from Madison Central and 81 students from Model. On a standardized test, the sample from Madison Central had an average score of 89 and a standard deviation of 4. The sample from Model had an average score of 87 with a standard deviation of 4. Calculate a 90% confidence interval for the difference in means. So here we have Minitab output. Notice under the descriptive statistics portion is the information from the two samples summarized. Under the estimation for the difference, we have the confidence interval. Notice this confidence interval is very similar to the one that we calculated by hand. There is a slight difference between the two, the main difference being in the degrees of freedom. When we calculated it by hand, we had the degrees of freedom be equal to the smallest sample size minus 1. But recall on page 17 in the notes, we know that doing this by hand is a conservative approach, and computer software can get a more accurate value. So looking at the Minitab output, notice that Minitab is using a different degree of freedom that we do, and this accounts for this slight difference in the confidence intervals. So if you were to compute this on an exam and you were given the Minitab output, your solution would look something like the following. You would need to do your assumptions check, similar to what we did before, state the confidence interval from the output, and then give the interpretation, which states we are 90% confident that the average standardized test scores for seniors attending Madison Central is between 0.877 and 3.123 points greater than the average score for seniors attending model. Next, we have this box from your book that goes over the summary of how to compute a two-sided significance test for comparing two population means. As always, when computing significance tests, we have our different steps that we go through, and here are each of those steps summarized. For your exam, you will not have to calculate the test statistic by hand. We'll do something similar to what we did when we looked at two proportions. For your homework, you can either use the MathCracker app, or for an exam, you'll need to read from Minitab output. So we're going to look at pages 21 through 22 in your notes, which use the online application to solve a problem. On the top of page 21 of your notes is a summary of how to use the website, and we'll look at the website together here in just a moment. We're going to use the example at the bottom of page 21 of your notes, which reads, a professor in the Department of Mathematics and Statistics at EKU is interested in the difference in final exam scores between developmental freshman math students in large lecture classes who are taught by different instructors. The incoming freshmen needing developmental services are randomly assigned to one of two instructors and are given the same final exam at the end of the semester. From the first instructor's class, a random sample of 15 students had a mean exam score of 82.45 and a standard deviation of 3.56. From the second instructor's class, a random sample of 17 students had a mean exam score of 79.89 and a standard deviation of 4.68. Is there a difference in the mean final exam scores between the two classes? Use a 0.05 significance level. So as always, when computing significance tests, we want to start with an assumption check. We take a sample of 15 students from one class and 17 from another. Both samples are smaller than 30. Therefore, the sample size requirements for the central limit theorem are not met, and we're going to proceed with caution. If we had been given that the samples from a normal population, we would have been okay, but we're not given that information. Additionally, the samples are not random. So you notice on the bottom of page 21, we have our two different hypotheses. Under the null, we're going to assume that the average exam scores for the two instructors are equal, and under the alternative, we're going to try to prove that they are different from one another. Page 22 looks at how to enter this information in the online applet. Here we have the online applet, and so we're going to go through and fill in the different pieces. The different pieces we fill in are given to you on the top of page 22. So we're going to start out by selecting our hypotheses. Under the null hypotheses, the two parameters are equal to one another, and under the alternative, they're different. Next, we're going to enter the information from our first sample. In our first sample, we had a mean exam score of 82.45. We had a sample standard deviation of 3.56, and we had a sample size of 15. In the second exam, in the second class, we had an average exam score of 79.89 and a sample standard deviation of 4.68 and a sample size of 17. We're using the significance level of 0.05. Again, and one other thing, we want to click that we're assuming unequal variances. Don't forget that this is a free application and does have ads in it, so be careful that you don't want to click on the ad. Do look for the Solve button. So we're going to click the Solve button. It might take it just a moment to run, but when it is finished, you'll see a solution set that looks very similar to the solution on page 23 of your notes. So scrolling down, notice here we have that solution. The first thing they're going to do is summarize the sample information, then give the null and the alternative hypothesis. Similar to when we worked with two proportions, we are not using the rejection region in this class, so this part is blanked out in your notes, but we do have the test statistic. This test statistic formula is slightly different than the one in your book, but for your homework, you can use this applet, and the test statistic you get should be very close to the one that you would get had you used the formula in the notes. So you can use this applet to work all of your homework problems. Also down here, they give us the p-value, and then our conclusion. So notice on the bottom of page 23 of your notes is the interpretation for this hypothesis test. It says at the 5% significance level, we do not have enough evidence to conclude that the average test scores differ between the two instructors. So again, you could use this applet on your homework for this chapter. On an exam, you'll want to be able to read output from Minitab. So we're going to look at what that would look like next for this problem. So here's what Minitab output looks like for this problem. Notice under descriptive statistics, we have a summary of the two samples. And then down at the bottom, we have the different pieces for the hypothesis test. And notice that that test statistic and p-value are very similar to what we found using the online applet. Let's look at another example together. In an attempt to determine if two competing brands of cold medicine contain on average the same amount of acetaminophen, 12 tablets from each of two competing brands were randomly selected and tested for the amount of acetaminophen each contains. The results are shown in the Minitab output, where we label brand A as group 1 and brand B as group 2. Since we have a randomized experiment, we may assume the assumption for random samples and independent groups are met. Additionally, assume that the populations are unimodal, symmetric, and bell-shaped. So as always, when computing a significance test, we want to start out by checking our assumptions. Assumption check. We have a sample of 12 tablets for each group. Since the populations are unimodal, symmetric, and bell-shaped, we can assume that the populations are normal and we do not need a large sample size. Additionally, we can assume independent random samples. Next, we need to set up our hypotheses. So notice here, under the null, the mean amount of acetaminophen between the two brands is equal, and under the alternative, we're going to try to prove that the mean amount of acetaminophen between the two is not equal. Looking at the computer output, we can see that our test statistic is equal to negative 3.52, resulting in a p-value of 0.003. Here we'll reject the null since the p-value is less than alpha. Then we'll give our interpretation or our conclusion in context. At the 5% significance level, we do have enough information or enough evidence to conclude that the average amount of acetaminophen does differ between the two brands. Section 10.4, Analyzing Dependent Samples. With dependent samples, each observation in one sample has a matched observation in another sample. Data is matched paired if the data is being compared consists of paired data values. Common paired data examples. Two measurements on each case compare each case to themselves under different treatments. So in other words, this would occur if you have one group of people and each person in that group receives both of the treatments. Twin studies. Each case is matched with a similar case, and one case in each pair is given each of the treatments. Any situation in which data is naturally paired. Consider the following two examples. Should data from the following situations be analyzed as paired data or separate samples? In a study to determine whether color red indicates how attractive men find women, one group of men rate the attractiveness of women after seeing her picture on a red background, and another group of men rate the same woman after seeing her picture on a white ground. Notice here we have two separate samples of men, each of those samples receiving a single treatment. This would be considered separate samples, and we could probably consider them to be independent and use the method we saw in the previous section. To measure the effectiveness of a new teaching method for math in elementary school, each student in a class getting the new instructional method is matched with a student in a separate class on IQ, family income, math ability level of the previous year, reading level, and all demographic characteristics. At the end of the year, math ability levels are measured. So here we have a situation of matched pairs, since each of the students is matched with a very similar student, and so each of the pairs receives both of the treatments. How can we analyze paired data? For matched pair experiments, we look at the differences between responses for each unit or pair, rather than just the average difference between the two treatment groups. We will construct a new variable consisting of the different scores. D stands for difference. For dependent samples, we can calculate the different score and then use the one-sample methods from Chapter 8 and 9. In Minitab, we use the paired t-test procedure to do this. So let's look at an example. Recent experimentation suggests that it may be possible for a person to control certain body functions if that person is trained using biofeedback. An experiment is conducted to show that blood pressure levels can be consciously reduced in people trained in biofeedback. The blood pressure measurements in millimeters of mercury listed in the table represent the readings before and after biofeedback training of 6 subjects. The recommended blood pressure is 120 or less. Here we're going to assume that those subjects are randomly selected, and this is written in your notes. Looking at the data, we have the following. Notice for each of the 6 people in this study, we have a before and an after measurement. In other words, each of the people have 2 measurements, and we can consider this paired data. So the data we're going to analyze is the difference between the before and after. So we can think of the difference as the single set of data that we are analyzing. Since we just have a single set of data here, and we're interested in the average difference, we can use our methods from Chapter 8 and Chapter 9. We're going to use Minitab to decide if there's evidence that biofeedback training helps reduce blood pressure at the alpha equals 0.05 level. We'll first check our assumptions. Notice here we have paired data with 6 pairs. We are given that the differences are normally distributed, so we do not need a large sample size. Also, we have a random sample. Setting up our hypotheses, we let μd represent the difference in before and after. Since we would like to prove that the biofeedback reduces the blood pressure, this would suggest that the before measurements are larger than the after, which would mean that we are trying to prove that the difference is greater than 0. So under the null, we assume that the average difference is 0 and try to prove that it's greater than 0. Using the Minitab output, we can see that the test statistic is 2.98 with a p-value of 0.015. Since the p-value is less than alpha, where alpha equals 0.05, we will reject the null. And then finally we have our conclusion. At the 5% significance level, we have enough evidence to conclude, on average, biofeedback helps reduce blood pressure. We could also look at the confidence interval. So here's the Minitab output for the confidence interval. We would need to check our assumptions just like we did with the hypothesis test. Then we could pull the confidence interval from the Minitab output, and we could say we are 95% confident that the mean difference before to after the biofeedback training is between 1.39 and 19.1 millimeters of mercury. This concludes the Chapter 10 video.